Welcome to part 5 for direct lookahead approximations. We're going to be doing stochastic lookaheads for problems with vectored value decisions. Okay, we're going to start with a technique called two-stage stochastic programming, and I'm going to illustrate this using a problem where two-stage stochastic programming has been widely used within the research community and the national labs. Let's imagine that I'm scheduling generators, nuclear power plants, steam generators, gas turbines. Maybe we have some wind farms in there, some solar farms, and some pumped hydro. Now, the utilities that do this, the gas turbines have to be planned a day in advance. And so what they have to do is typically around noon, they'll fire up a big model that plans roughly 48 hours in the future, but they're mainly planning for tomorrow. And tomorrow, there's going to be various forms of uncertainty where they have to handle this. Now, what they've been doing is, in practice, is using a deterministic lookahead, but the research community has suggested that they handle uncertainty, and I'm going to describe how they do this. Now, the basic planning process in grid operators is you have a day-ahead planning process, which is slow. This is generally run once a day, planning for tomorrow. Then there's other decisions. Intermediate term gas turbines are planned about an hour into the future. So these are decisions where I can actually wait until tomorrow. But when I'm making the day ahead decision, I have to think about the gas turbines. And then there's real-time planning where I can do adjustments of gas turbines as well as the steam generators. I can make small adjustments. I can't turn a steam generator off and on instantly, but I can make small adjustments. Now, the day-ahead unit commitment problem is you sit at noon and you're planning roughly, you want to plan midnight to midnight. They extend the model further out so that there isn't a truncation problem. And this is done on a rolling basis. The intermediate term problem is solved maybe once every half hour. So at 1:15, they'll fire up something. They'll be optimizing literally from 1:30 to 2, but then there's some roll ahead. And this is also solved on a rolling basis. Now, the look ahead problem, if they're planning steam generation, what they're going to do is output from the run on noon the previous day, they're going to output an actual schedule for each steam generator for tomorrow. And that includes when it fires up. They don't turn off and on instantly. There's a ramping up and ramping down period. And so they come out with a schedule for all the steam generators for tomorrow. This is a fairly hard problem, but advances in integer programming have helped this. Now, let's imagine that they're handling uncertainty from some stochastic source. Here, I'm going to assume it's wind because they started to get very interested in handling the uncertainty of wind. Now, that black line is the forecast, but the reddish line would be, well, this is one sample realization of what might actually happen. Now, what they're going to do is have a series of scenarios. So the black line here, there's one black line, and each scenario will have a different possible outcome of what can happen with the wind. So that slight reddish line will be different for every scenario. Now, what we're going to be doing is setting up a problem where we're optimizing all the steam generators. So that X there, XT, is a very big vector. This is, and it has a lot of integer variables because you have to have am I turning it on, yes or no? And then you'll have other continuous variables. Now, at time t, that is, let's say Monday, I'm going to be scheduling the steam generator. So when you look at that xt, it's not a scalar anymore. Now it's a very large vector. Now let's imagine that we are going to try to incorporate that one of, let's say, 5 different wind scenarios might happen. So we're going to denote those by omega 1 through omega 5. Maybe they do 20 scenarios, but let's just do 5. That set of scenarios is considered a set of outcomes, capital omega. I don't know which one of those is going to happen, but what I'm going to do is I'm going to incorporate all the possible scenarios into this one big model. So I'm going to have decisions. If you look at the objective function in the upper left there, xt is the decision I'm making now that will be implemented. Now the x tildes are the lookahead. Notice that I have the tildes. I have a tt prime because I'm making the decision at t, but thinking about t prime in the future. And that omega is the sample path, omega 1 through omega 5. But notice how I've put it all into one big problem, because the decisions that I can make tomorrow, the x tilde decisions, depend on the decisions xt that I make today. So they're all coupled together. So I have to put it into one big math program. Those scenarios is when I'm scheduling the turbines, so you can think of those future decisions as the turbines. By the way, the general field of stochastic programming, I say probably the go-to reference is the book by Burge and Louveau called Introduction to Stochastic Programming. Now, when you look at the stochastic program, the optimization at time t, I have two sets of decision variables. I have the xt, and those are the variables that I'm going to implement now. But they're coupled with these x tilde variables, and I have one of those for each omega. Maybe I have 20 omegas. In practice, it's a number like 15 or 20. And the x tildes, those are actually the gas turbines, because I'm not planning steam generators for tomorrow. I'm planning the gas turbines. Now notice it's all one big problem. So remember that xt might have, I don't know, 10,000 elements in it. I mean, this is a fairly large vector. The x tildes may also have a different number, maybe smaller, but still not small. But I have to optimize over all of them all at once. And the x tildes, you take however big it is, maybe there's 1,000 elements, and then multiply it times the number of outcomes, omega. So this is quite a large problem. This is part of what has limited the adoption in practice. There's other issues. But there's an entire community of people who develop and further explore research in this area. This particular technique literally dates back to 1955. George Dantzig introduced it. It started to really kick into interest in the 1990s when computers became faster. It's still a look-ahead policy. So at time t, I'm going to look ahead. I've got the decisions to be made now. That's a vector. I've got all the scenarios in the future, and those decisions are vectors as well. But it's still a look ahead. So I do this look ahead on Monday, then I roll forward to Tuesday and do it again. Here's Wednesday. Now, in practice, it's quite rare to simulate a look-ahead policy based on scenario trees, but some people do it, okay? So if you look at Burge and Louveau, they will never present this optimization problem as a policy, but some people, not everyone, will simulate it, which means they're acknowledging that it is a policy. So there's a fair amount of confusion in the stochastic programming literature. Let me approach this problem from a different perspective. Remember, x is still a vector. I can view this whole look ahead as a giant function, and it's a function of xt. Now, there's a bunch of other x's in there, but those are going to be handled by the policy within the policies. And I'm going to be simulating, I'm going to call that simulated information w tilde. I'm going to index it by t plus 1 because it's not known at time t. If I just roll all that together, I can just call it a big function. Let's call it a simulator, where if I set xt and then simulate it, and of course this assumes that I have a pi tilde, the policy within the policy. Now I can write this whole stochastic lookahead as a stochastic search problem. Optimizing this f tilde, I call it f tilde because it is a lookahead. Remember, notice that xt doesn't have the tilde because that's the decision I'm going to make now. Now, again, xt is a vector, but we have tools for solving this stochastic search problem. A natural choice is Jim Spall's SPSA algorithm. I'm going to cover this. I'm going to describe that in the module on policy search. So I'm not going to go into details here, but watch the module on policy search. Spall's SPSA algorithm is really quite elegant. Most of the algorithm fits on a single PowerPoint slide, and it's not that hard to code. Using it will have its own technical difficulties. Okay, thank you very much.